YOLO Composing Gloves here, and today I know you're wondering about, like, if you had asteroids that form a right triangle, what would be the net force on the third one in the corner? You know, that one right there. I know you were wondering this, so we're going to talk about that. So okay, let's back out here. We say, well, net force, what exactly are we asking for? So we see we have these three asteroids. They are positioned in such a way that they form a right triangle, and we want to know the net force on this guy. So we're basically saying, hey, if you had to draw one vector coming from this object that would show where this thing's going to go, what vector would you draw? That's the net force. And so we ask ourselves another question. Well, we say, okay, what laws are we going to need? Well, we're going to need the law about the inverse square law that uses gravity. It's this thing over here. These are all good examples. So the force of gravity, that's what this is, between two objects, because of the universal law of gravity, is going to be the universal gravitational constant times the two masses over the distance squared. So I'm assuming you're already comfortable with this to a degree. And so we say, okay, that's the law we're going to need. So we say, all right, well, we know there's going to be a force from there to that asteroid, right? These two asteroids will have a force on each other. We only care about this one in the corner, so we're only going to worry about that one. And we know there's going to be a force between these two. Now, if we make our x-axis like this, boop, 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 and our y-axis, we've got one on the x-axis, but the other one we don't. So we're going to need to break it into vector decomposition like that to a degree. This is really just like a quick sketch. And we say, okay, well, that means that the net force on this asteroid is going to be the force in this direction and the plus the vector component, this vector component in that direction, plus the vector component in this direction. And that will give us our net force. And we'll also need to know the angle at which this force is applied, which we will be able to solve for as well. So that's basically what we're doing. And I actually have this labeled over here somewhere. I have net F3. We could write this. Well, I don't want to blow you away quite yet. So let's go ahead. Let's just start solving this one step at a time. But basically, that's what we're aiming for. It's what we're looking for. So we say, okay, we're given these three asteroids and we're given two distances. And we're told that they form a right triangle. So we say, all right, here are the three masses, M1, 2, 3. And here are and I list their masses. And then I list the distances as R, 2, 3 and R1, 2. So what's this deal? So this is the distance between asteroid 1 and asteroid 2. It's 40 meters. And that's sort of the idea. Maybe you could label them ABC and then use letters, because later on we will be using exponents. And in my experience, exponents and subscripts can get a little confusing sometimes. I don't know about yours. So we're going to be using this though, because it's a really easy way to specify between what distances we're talking about without having, I don't know, I'm not sure of another way to really write this effectively. So we say, okay, that's what we're going to use. So we have our distances labeled in R, just because R is commonly used for distance, radius, stuff like that. And then we have our universal gravitational constant, which we list in the given. We're just letting people know, hey, we're going to use this thing. And then we're looking for our FNet 3. If we had to draw one vector that showed the direction this thing's going to move, how would we draw it? So next up, the next easy step is we're going to make a free body diagram. And in our free body diagram, we're just going to label all our forces before we even worry about equations. Let's just worry about getting all the forces we can think on there. And this actually is not that bad. It's mostly just one vector resolution and one vector in reality. It just gets bad because we have to have everything in terms of our given. So we say, okay, we draw our three asteroids, asteroid 1, 2, and 3, and I drew a dotted line triangle to show that they form a right triangle. So I say, okay, there's our right triangle. And keep in mind that these are distances. So I labeled the distances R1, 2, R1, 3, and R2, 3. So far, so easy, right? And I say, well, in this triangle, there's some angle theta. So I went ahead and I noted theta here in red. And I said, all right, that's the angle theta. And let's go ahead and do our forces. Now, we only care about the forces acting upon the third mass. So the other masses, thankfully, are blank. I had a problem that asked for two of these. And I was like, you got to be kidding me, man. It ended up being a long problem just because of all the extra little lines everywhere. So anyways, we have a force, right? According to gravity, there's two big forces going on. They're the ones in green. We have a force, so this F here, from 3 to 2. So this is the force 2. We're going over to 3. So we have a force going on here. So that's F3, 2. and it's going along towards M2. And at this point, I was like, let's do our x-axis and y-axis. Seems like a good idea. So you can see here I have my x-axis labeled and my y-axis also labeled. So I say, okay, cool. We've got our x and y-axis. And I say, look at this. F32 is already on the x-axis. So that's great news because I know how to work with x-axis vectors. So we could just leave it like that. But we have another force here, and that's the force between M1 and M3. And just a quick reminder, by the universal law of gravity, between any two objects, there is a force of gravity. However, this force of gravity only really matters for very massive objects because the force is so small. It's the reason why everything around you isn't flying at you, because it's a very small force. We're going to talk about this in the equations. But anyways, we have this force going between these two objects and those two objects. But the bummer's thing about F31 is this is at some angle, and we don't know how to work with that. So we need to do a vector decomposition. So you can see here I drew an altitude. I actually did a pretty decent altitude finally in one of these pictures. And we resolve it. I say, well, if this is theta, I could take this and move it over here so it would appear right there. And so that would make this sine theta. This is just an easy one to quickly explain. And this one would be cosine theta, right? So now we've broken up F31 into F31 sine theta and F31 cosine theta. And so now we've got our two vectors. And so now we say, oh, I see it now. If we want to know the sum of all the forces acting upon this object at the angle theta, we're going to have a force F32 plus the force F31 cosine theta plus the force F31 sine theta at some angle theta. And so we say, wow, okay, that's just a lot to say. So let's go ahead. Let's start looking at some additional equations. But before we go there, let's really quick define a couple of things. So let's figure out what R13 is. So if we come over here, we have R12, R23, and it's a right triangle. So that means R13 is going to be the square root of these two distances squared by the Pythagorean theorem. So this is really easy math. I'm not going to say much more, but we're going to use this instead of R13 because we got to use only stuff that's in our given. So it's sort of I don't know. I feel it's a little silly, but that's what we got to do. In reality, you could solve for the number and just plug that number in wherever you see this, but whatever. So that's what we got going on there. And also we need to differentiate this angle from the angle of our forces. So our forces are actually, our force may not necessarily come off at that same angle. So we're going to use this second triangle. So here's our force Fnet 3, right? That's going off somewhere. And we say, well, Fnet 3 was going to be Fnet 3x, Fnet 3y. And that's at the angle alpha. And I just want to demonstrate this to you now. And these are right triangles, right? So I want to show this to you now because we are going to call upon this information later. So we define this angle as alpha and this one is theta because the distances may form one angle, but the forces may not. So we need to be careful about this. If you have a more symmetrical shape like a square, this isn't really a problem, but a lot of the times you don't. So if we had a square, we'd have to consider other forces. We'd have to consider across it and then up it, and yeah. So, okay. So first, let's just go ahead. Let's do the easy one, F32. F32 is super easy. And so we say, okay, we come up here and we say, here's F32. And we say, all right, F32, and then we draw out our law of gravitation. And so we say, okay, here's the G, and then the product of our two masses, M3, M2, over the distance squared. So the distance, R23 squared. So that's not too crazy. That's going to be the force. So there we go. We've got our force solved. So we've already got this green vector taken care of. And now we say, well, let's take care of some of the other vectors. So we come over here and we say, okay, well, F31 is equal to, so if we come over here, F31, that's going to be equal to G M3 M1 over R13 squared. However, this is going to be at some angle. So this definition we can't use because it's at some angle. And so I say, okay. I wrote this one. Oh yeah, okay. So here I wanted to differentiate that we can't write this because we don't know that technically. So that's where this thing came up. And since it's the distance squared, the radical goes away. So we're actually writing this, but the radical went away because it's the distance squared. So that squared actually disappeared. So this is our F31, but again, it's at an angle. So we say, all right, well, let's figure out what this is. So we say, let's refer to our Fnet. So how do we find Fnet3? So this Fnet's not the same thing as this F31. This is the net force. So we say, what is the net force on our object 3 on the x-axis? So that's what the 3x is. And we say, well, on the x-axis, there's a force F32, this guy, which we have already solved for. And there's a force F31x. And we say, we know F31x too. F31x is, that is simply, if we come down here, that's actually going to be the cosine alpha. F3 cosine alpha will give us our Fnet 3x. And according to our angle of distances, we actually solved for it as F31 cosine theta. So we say, okay. So we come on down here and we say, well, here's Fnet 3x. But before we do that, we got to figure out what this angle theta is. So I know it's just like one thing after another, but none of it's actually a complicated step. It's mostly just keeping track of where you are. So we say, all right, if this is theta, and this whole thing is a triangle, we can use trig to figure out this theta. So we come over here and I said cosine theta, right? That's equal to, if you remember your Sakatoa definitions, we take our cosine. So this distance R23, and that's over the hypotenuse R13. And that's simply cosine. So now we've found theta. So I have cosine theta is R23, and now we can't write R13, right? Because that's not in our given column. So we have to write this crazy square root sign. And that's going to be the angle, right? So there we go. We got our angle, cosine theta. So now we can simply plug this in whenever we need cosine theta, which is really handy dandy. So we come over here to F3x and we say, well, the first mass is going to be, this is just going to be F32, which we solved for up here. So that's not crazy. And then the second mass, which is F31. So this is the F31 definition, but we need it at the angle theta. So we have to multiply this times the angle theta, which we just solved for. And boom, you get Fnet 3x. So this is Fnet 3x, like holy crap. And if we want the full Fnet, I don't think I ever wrote this on here, Fnet 3, right? That's going to be equal to Fnet 3x plus Fnet 3y. So we just have to add our two. This should be like a subscript 3. Looks kind of large. The y does too. Anyways, it's just going to be those two. So we've already got Fnet 3x right here. It's kind of long. And then we say, well, Fnet 3y, what is that deal? So we say, well, Fnet 3y is just the forces on the y-axis. And we notice we only have one. It's this. Fnet 3.1. Now this one's a sine theta. So sine theta is not the same thing as cosine theta. So our thing is going to change a little bit. Instead of having 2, 3, we're using 1, 2. Because it's going to be the opposite. So this is the opposite side. And we're still going to have the hypotenuse. So we're still going to have this ridiculous square root thing down there. So we're going to have our gravitational constant with our mass 3, mass 1 over, and then unfortunately in this case we have this crazy r squared. It's r31, right? But we can't write that. We have to write this thing, and it's squared. So same as this deal right here. And whoops, that's music. We're not talking about music right now. And then we say r23 over the square root of this. So this is our definition of, whoops, that's x. This is our r12 over this is just our definition of sine. So that's just sine theta. And we say, okay, cool. If that's sine theta, Fnet 3. Now this is where we bring up this triangle here. So we say Fnet 3, if this is Fnet 3 right here, and it forms a right triangle, and we could picture this being moved to being right here. That doesn't change nothing. This is a similar move as just regular old vector decomposition. So we say, okay, Fnet 3 is going to be equal to the square root of these things, right? Because Fnet 3 forms the hypotenuse of this right triangle. And then we say, all right, well, we know Fnet 3 and we know Fnet 3y from up here. So we simply plug those in. So you write out this massive thing under a square root, this whole thing squared, and that is literally Fnet 3. And so we say, holy friggin' crap, that's huge. And yeah, it kind of is. That's just that's what it is though. So there you go. That's why I'm saying you could plug in numbers if you want. I mean, be my guest. It's just going to be quite a long plugging in process. And then we say, well, okay, but we still need to know the angle alpha, because the angle alpha might not be the same as theta. And so if you could see here, if we come over here to our FNet3, what is the angle of FNet3? The reason we're using theta for these is because that's what these forces are at. But the FNet force may not be at that angle. The FNet force may be at some other angle. So we say, okay, no problem. We say alpha inverse tangent. Okay, well, first let's just look at this. So we say, okay, here's this. Here's the angle alpha. We say, well, let's just use, we can't use the hypotenuse because that's what we're looking for, is the angle of that. And we don't know, well, now we know this, but I don't want to rewrite this enormous thing. It's crazy. So I'm going to use tangent, because tangent will use this side and this side. And that's really easy. So this is just FNet3y and FNet3x. And it's always, for tangent, it's always y over x, right? So we say FNet3y over FNet3x. And then you write out this big thing, because you know FNet3y and FNet3x from up here. And then if you take an inverse tangent, you'll actually get the angle alpha. So you can get alpha out of this as well. So you can say, well, if you wanted to, you could plug it into this big thing, and you could get FNet3 and the angle that FNet3 is being applied at. And you could draw that vector exactly and tell them exactly how far it would go, and it would be super duper. So anyways, that's how you take care of problems like this. I've seen a couple variations where they throw additional objects at you. One thing you want to be careful of when you claim angles is, I've seen some people, they just sort of say, oh, this is the angle because these things are all symmetrical, and so it would have to be this. And usually there's that can work, but it's not always the most rigorous way of doing it. So sometimes it's better to just pull out inverse trig. Usually you can prove it just this is it for sure 100% with inverse trig. Instead of going, I'm pretty sure I remember this geometry theorem thing. Other times it's really easy. Like if you have like a square, it's kind of like a toss up whether or not. I always go with just like the crazy, this is exactly it way that I can think of, because then the teacher can't dispute it. You never know. Maybe your teacher has some interesting ground rules. So anyways, yes, subscribe and have a blessed day.